so.
Okay. So we talked about the steps to do a hypothesis test.
Yes, yeah.
And then we talked about the difference between statistical and practical significance. So how do we actually go about doing a hypothesis test? So we talked about the steps, but now let's talk about how we're going to do this. So we're going to take the same approach we took in chapter 8 with confidence intervals. We're going to start off assuming we know the standard deviation of the population. Now, is that normally the case? Is it normally the case that we know the standard deviation of the population?
No, not always.
Right, but there are circumstances where we might either know it or have an idea of what it should be. Okay, and so there are a few circumstances where we can make this assumption, but for the most part we can't. So we'll get on to that hopefully either by the end of the class today or at the beginning of class next time. So when we know the population standard deviation, our sampling distribution is normal. Excuse me. And sometimes you may hear this referred to as a z-test. Okay, when somebody talks about a z-test, they're talking about a hypothesis test where the standard deviation of the population is known. Okay, and so there's a couple of ways that we can do this. Okay, so the way the textbook does it is they will ask you to compute a test statistic. And whenever you're asked to compute a test statistic, they want you to do this. This is the test statistic. Z-calc is the test statistic. Okay, it's basically the sample statistic converted to a z-value. And we've done z-values. We've done z-values a lot. We started doing z-values back in unit 1, and we did them in the last unit. So do y'all remember how we calculate z-values?
It's the norm dot s dot inverse of the alpha.
Okay, so hold on to that, but that's not what we're doing now. What we're doing is determining what is the z-value that represents our mean, our sample statistic. So we're converting a real world value into a z-value. How do we turn a real world value into a z-value? Think about how we've done it in the past. This is one of those where I told you to learn the formula, and if you don't remember the formula, you may have problems in the next class because they're not gonna stop and say, oh, you don't know that? Well, let me teach you that. Right? In the next class, you've got an hour and 15 minutes each 2 times a week to cover all the material. And there's not time to go back and say, well, you don't know that, we're going to fill you in. You're going to be expected to know it. So what's the formula for computing a z-value? Somebody tell me, please.
Would it be the alpha divided by 2?
Nope. Nope, the z-value is not a probability. It's not an area. It's a value. What does the z-score tell us? What's the interpretation of a z-score?
Standard deviations from the mean.
Exactly. How many standard deviations we are from the mean? Well, how many standard deviations we are from the mean? Well, we're this far from the mean. And if we divide by the standard deviation, that tells us how many standard deviations we are from the mean. Everybody should know this. We learned this back in Unit 1. We learned this back in Unit 1. Does everybody remember that?
Yes.
Okay. So this is how we convert a value into a z-score. Okay, so I have some real world value and I want to turn it into a z-score. Is everybody okay?
Yeah.
Notice that what we're talking about here is we're talking about our hypothesis test, where we have a hypothesized mean, and I'm just going to draw it over here. It doesn't matter where I put it. And we've got some sample mean. And what I want to do is I want to convert this into a z-score. And this is how I do it, right? I take the value I want to convert into a z-score, I subtract off the mean, and I divide by the standard deviation. Is everybody following?
Yes.
Okay, so remember, when you're doing hypothesis tests, we don't have a function like confidence.norm that's going to do all the work for us. We've got to know how to do the work. And according to my students who come back from Cal State San Marcos, they all tell me this is the first thing you do when you take your next class. The first thing they're going to do is jump you right into hypothesis testing again. So given that we want to do this, how do we do it? Well, we want to get a z-value for our sample mean, where the mean of the population is our hypothesized mean, and the standard deviation, because what is this distribution?
Normal.
What?
Is it normal?
No. What is it that I told you in the last chapter about every time you see one of these, what is it?
Sample.
Think it's a sampling distribution. What is the standard deviation of the sampling distribution? What do we call the standard deviation of the sampling distribution?
Standard error.
Standard error. Notice this is that. That's all we're doing. We're applying that formula we learned way back in chapter one in unit 1, way back in unit 1, to computing a z-value for our test statistic. Does everybody understand that?
Yeah.
Okay. And how do we do this in Excel?
Standardized.
Yeah, we use the standardized function. Right? We use the standardized function. So we'll compute the calculated z statistic, okay, the test statistic that they're going to ask you to compute. You're going to use the standardized function. Does everybody understand that?
Mhm.
Yeah.
And so, as we said, we generally don't know this. So we, like we did in the last chapter, we'll use our sample standard deviation, which means we'll use a t-distribution instead of the normal distribution. And we'll talk about this again, either at the end of class today or next time. Okay. Are we okay?
Yeah.
Yeah.
So let's do some practice. Okay, let's do some practice and recognize that in order to do a hypothesis test, we have to do two things, right? We have to do two key things. And we saw these pictures last time of the different kinds of hypotheses test, a right-tailed, left-tailed, and two-tailed. Okay. So there's two things that we have to do, right? One, we have to compute our critical value, right? That's the value that has alpha. If it's a right-tailed test, it's alpha to the left of it. If it's a left-tailed test, it has alpha area to the right of it. If it's a left-tailed test, it has alpha area to the left of it. And if it's a two-tailed test, it has half the alpha in each tail. So how do I compute a z value that has alpha or alpha over 2 in the tail? What's the function I use in Excel to compute a z value?
Would it be the inverse one?
Yes, that's exactly right. Right? Norm.s.inverse. Because here I have probability. These are not real world values. These are probabilities. Right? We did a bunch of these in chapter 7. Remember all that practice we did in chapter 7? That wasn't just, to punish you or to make you do stuff because it's fun to make you do stuff. That was to get you used to doing this, because now we're doing it in the context of a hypothesis test. We've got to be able to compute the critical values. And to compute the critical values, we use an inverse function because we know the probability or area. Is everybody okay?
Yeah.
Okay. The other thing we have to do is compute our test statistic. And we just saw how to do that. And then we'll compare our test statistic to the critical value and determine whether we reject or not, right? If the test statistic falls in the rejection region, we're going to reject. Everybody okay with that?
Mhm.
Okay. Okay. So we're going to practice doing both of those things. First thing we're going to do, we're going to go to our workbook. And the first thing we're going to do is practice computing some test statistics. So we'll scroll down and look at that. Practice 9-13 says, find the zCalc test statistic for each hypothesis test. So let's write down what information they give us here. They give us the sample mean, X bar. They give us the hypothesized mean, mu naught. They give us the standard deviation of the population, and they give us the sample size. So we have 3 scenarios here. Okay. The first one, so what's going on here? So we have our sample mean. So we've already taken our sample. We know what our hypothesized mean is. we know the population standard deviation and we know the sample size. So let's type that in for this first one, 242, hypothesized 230, standard deviation 18, sample size 20. So how am I going to calculate the test statistic?
We're going to choose the standardized function.
Yeah, we're going to use a standardized function. I mean, we just spent like 10 minutes talking about computing the test statistic. Right? This is where 10 minutes ago I told you the sky is blue, and now I'm asking you what color is the sky. And if you don't know what color the sky is, then you should have been asking questions when we were talking about the sky is blue. Okay, you've got to understand this, because you're going to be expected to know it not just for this exam, but in your next class. And your next class is not a lower division class. It's an upper division class. Okay? And I guarantee you, if you've never taken an upper division class, most of you are in for a really big surprise, and it's not a good one. Okay, it's not a good one. I've had students come back and tell me that my class they took was the hardest lower division class they ever took, but it was nothing compared to the upper division. Not necessarily workload, but difficulty. Okay, if you want to succeed, you've got to learn this. Okay, so do I have enough information to use the standardized function to compute my test statistic?
Yeah.
Are you sure?
Oh, is it that we're using X bar instead of the actual mean?
No?
We need just X, mean, and standard deviation for standardized, correct?
Yep.
All we have is X bar, standard deviation. Would N be X in this particular situation? Is that two different meanings in this?
No, let's go back. Let's go back, make sure everybody's understanding. Okay. The standardized function computes a z value. You give it an X, you give it a mean, and you give it a standard deviation.
Right.
Okay. What's the X in this case?
In our case would be X bar, right?
Exactly.
Oh, okay.
Is this? What's the mean?
Mu naught, which we have.
Exactly. That is this. Okay. What's the standard deviation?
We have to adjust it. Our standard deviation would be the standard deviation of X bar.
Which is, what do we call that?
Standard error.
Standard error. So this is standard error. Do I have X bar?
Yeah.
Yes.
Do I have mu naught?
No.
Yes.
Yes.
Yeah.
Okay, look at the spreadsheet. Yes, I do. Do I
But we don't
have standard error?
No.
No. Okay, so remember we talked a little bit about this. I kind of gave you this warning, I think, back in chapter 8, that when we do confidence intervals, we didn't have to compute standard error directly because the confidence function does it for us. There's no function to do the work for hypothesis testing. We have to do the work, which means we have to compute standard error. Okay, so you want to remember that, right? You want to remember that, put that kind of in the front of your brain. Okay, remember that when we're doing hypothesis testing, we have to compute standard error. Okay, because standard error is the standard deviation of the distribution we're using because we're using the sampling distribution. Is that making sense to everybody?
Yeah.
Okay. So the answer to the question I asked before was no, we don't have everything we need. We need one more thing. We need standard error. How do we compute standard error?
We take the standard deviation divided by the square root of n.
Exactly. Standard deviation divided by the square root of n. And you're going to hear that question like 50 times between now and the end of the semester. Okay? Because this is something you've got to know. Okay? There's our standard error. Now I've got my x value, I've got my mean, and I've got my standard deviation. So now I can compute my z-calc, which is my calculated test statistic. Okay? It's my z-score that represents this value. Okay? And you may be able to look at that and see this number is going to be just a little bit below 3. So let's do it. We'll standardize where my x value is my sample statistic. My mean is the hypothesized mean, and my standard deviation is the standard error. Are we okay? Okay. And there we go. We get a number a little bit less than 3, just like we expected. And I think in this one, let me double check, make sure I do the rounding the right way. I think in this one, they rounded to 2 decimals. Yeah, in this one, they rounded to 2 decimals. So that's what I'll do. So there's our answer. Okay. So this is the test statistic that we would compare against our critical value to determine whether we reject the null hypothesis or not. Is everybody okay with that?
Mhm.
Okay. Now the next one. The next one says our mean, our sample mean is 3.44. Our hypothesized mean is 3.5. Our population standard deviation is 0.24. And we got a sample size of 40. Okay. Now, what do we need to do?
Find a standard error.
We need to compute the standard error. Well, the formula is the same, so I can just copy it down, right? And I get standard deviation divided by the square root of the sample size. Okay. Now the question is, what can you tell me about this number? Before we even do the standardized function, what can you tell me about that number?
It's less than 1.
Yeah, well, yes, it's not less than 1. It's negative. Does everybody see that this number is going to come out to be negative?
Yep.
Okay. Why is it going to be negative?
That's the x bar minus the, so it's 3.44 minus 3.5. It's going to come out to a negative, and then we divide that by.
It's because the value that we're trying to get the z-score for is less than our mean, isn't it?
Yeah.
Right?
And then dividing it by a positive number will just create a negative.
Yeah, exactly. Dividing it by a positive number isn't going to change the sign, right? Remember, what's the mean of the standard normal distribution?
0.
It's 0. So when we're trying to convert a value into a standard normal value, a z-score, values above the mean come out to be positive, and values below the mean are going to come out to be negative. That's a good thing to keep in mind, because sometimes we want this to be negative, and other times we're going to want it to be a positive number, even if we are dealing with a value to the left of the mean. Okay, so we want to be careful about this. So I'm going to do exactly the same thing I did. So I could just copy that down, and there's my z-score, right? This is 1.58 standard errors below the mean. And again, we would then compare this to our critical value to see whether we reject the null hypothesis or not. If this is in the rejection region, we reject the null hypothesis. Otherwise, we don't. Is everybody okay?
Yeah.
And then the last one, 21.02 is our sample mean. Our hypothesized value is 20. Our population standard deviation is given as 2.52, and we have a sample size of 30. So what do we do first?
Find the standard error.
Find the standard error. So again, the formula is the same, right? I don't need to retype it in. I can just copy it down. Standard deviation divided by square root of sample size. And then what's our z-calc going to look like? Well, which side of the mean is this on?
To the right.
It's to the right. So we're going to get a positive number. And if you kind of look at that, you can see that's one above, and that's about 0.5, maybe a little less than 0.5. So it's going to be a little more than 2, isn't it?
Yeah.
Okay. And so if we compute it, we get a number a little more than 2. Okay. Whenever you can look at things and say something about the result you're going to get, then you have a way to check it for reasonableness. If I'd gotten a negative number here, I would know I made a math error somewhere, right? Because this can't be negative if the number I'm trying to standardize is above my mean. It can't be negative. It's impossible. Okay. Is everybody okay?
Mhm.
Okay, so make sure you understand how to do this. You're going to have to do this in most of the problems. Okay, most of the problems you're going to do, you're going to have to do this calculation. So make sure you understand how to do this. Is everybody okay?
Yeah.
Okay. The second thing we have to do is calculate the critical values. Okay, so our next practice has us calculating critical values. Okay. So it says use Excel to find the critical value for each hypothesis test. Okay. So notice that, what do they give us? They only give us alpha. Right? They only give us alpha. And from that, they want us to compute the critical value. So I'm going to do a little copy here, so I don't have to redo this whole thing. Oops. Wrong one. Okay. So I believe they usually refer to this as, for the critical z value, z-crit. Okay. I usually like to refer to them in terms of lower critical values and upper critical values. I usually like to refer to them that way. So they'll usually use this, and I like to use this because I think this is more descriptive and a better indication of what we're doing. And we have 3 tests here. Okay. So question 1, how do we do this? How do we do this? So
Use the inverse function.
yeah, well, so let's think about this for a minute, right? So I've got my alpha, so you know I'm going to use the inverse function, and this is a 2-tailed test. Okay, this is a 2-tailed test. So what should we always do?
Draw a picture.
Draw a picture. So I'm going to go back and let's draw a picture of this. Okay, let's draw a picture of this. Okay, so we're using the standard normal distribution, right? So this distribution is going to have a mean of 0. Okay, and we've got a 2-tailed test. So a 2-tailed test, remember from the picture, All right, remember from the picture, you should refer to page 6 anytime you need to. Remember from the picture that in the two-tailed test, half of alpha is in each tail. Right, so I'm going to have a value here that I call the lower critical value, and I'm going to have a value here, which is called the upper critical value. Okay, and these are both going to have how much area in the tail?
Alpha over
Point.
2.
Alpha over 2. What's our alpha?
Alpha is 0.05. Alpha over 2 is
0.05?
0.025.
0.025. So each tail is going to have alpha over 2, which is 0.025 in each tail. Is everybody okay?
Yeah.
Okay. Okay, now what we need to do, because we have our test statistic as a standardized statistic, what we're going to need to do is we're going to need to come up with our critical values. Okay, I'm going to come up with a critical value there. And what do I know about this critical value compared to this one?
It's just the negative of it.
That's right, right? Because of symmetry, this is just going to be minus, right, of whatever that is. So does it matter which one we find?
No.
No.
You find either one because the other one is just the negative of it. Which one do you want to find?
Let's find the upper critical.
Okay, so how would I do this, right? So this is saying, right, this is saying, and I'll do it in standard normal terms, this is saying the probability of getting a z value greater than some value here, my critical value, is equal to 0.025. And so somebody already said, what kind of function do we use to do this?
An inverse function.
Inverse function, right? So we're going to need to use an inverse function. Since this is standard normal, what inverse function do we use?
Norm.s.inverse.
Exactly, norm.s.inverse. Okay. Can we do a greater than?
No.
No. So what do we have to do?
Make it less than or equal to.
Yeah, and
Oh, that'd be 1 minus the.
do the complement, right? We need to do the complement of the probability, right? This is the critical value. Okay, so that's just doing the complement rule. And so what we need to use is we need to use 1 minus half of alpha. Does everybody see that?
Mhm.
Okay. So if we go back to our spreadsheet, okay, so our alpha here is 0.05, okay, and our critical value, norm.s.inverse of 1 minus alpha over 2. Is everybody okay?
Mhm.
And there is our critical value. Okay, and you may recognize that number from seeing that before. Let's see which one we're doing here. Oh, that's the one we're doing. So they did 2 decimals on this one. So I'll do 2 decimals on this one. Okay, and so our lower critical value is just minus that, and our upper critical value is just plus that. And so there are the answers for the first one, right? What are the critical values? The critical values are negative 1.96 and positive 1.96. Okay. Negative 1.96, positive 1.96. Those are the 2 critical values. And so now when we get our test statistic and we compute the z value for our test statistic, we'll look to see, does it fall below that or above that? If it does, we'll reject. If it doesn't, we won't reject. Is everybody okay?
Yeah.
Awesome. Okay, the next one gives us an alpha of 0.1, but this one is a right-tailed test. So again, let's draw a picture. Okay, since we're using the standard normal, our mean is going to be 0. And it's a right-tailed test, okay, which means the alpha's in the right tail. So we've got some critical value here. Again, I call it an upper critical value, so because I know it's above the mean, okay, that has how much area in the tail?
.1.
Yeah, all of alpha's in this tail, right? We don't have to split alpha because this is a one-tailed test, right? This only has one tail. So all of the alpha, right? All of the alphas in this tail. And again, I'm going to want to compute a critical value, okay, in terms of a z value, where this is the probability that I get a z value greater than my critical value is 0.1. And so we've got the same situation. Can Excel do a greater than?
No,
No. So how do we do this?
you use the complement rule.
Use the complement rule, right? So we can say the probability of a value being less than or equal to, it doesn't matter because remember we're using a continuous distribution, so it doesn't really matter whether you do that or not. Is the complement of that 1 minus 0.1, which is 0.1. Is everybody okay?
Yeah.
Okay. And then now we can compute our critical value, right? Because we know it's going to be norm.s.inverse of 1 minus our alpha. And again, they went to do decimals, so I'll just do this as 2 decimals. And in this case, we only have an upper critical value because it's a right-tailed test. So I'm going to put that there. Okay, because that's the terminology I like to use. Are we okay?
Yeah.
Yeah.
Okay. And then the last one says we've got an alpha of 0.01, and now we're doing a left-tailed test. So we'll go back and draw another picture. And again, we've got our standard normal distribution. So the mean is 0.
To quickly refresh,
Yes.
a two-tailed test is the equal, not equal. A right-tailed test is one of the greater thans, and then left-tailed test is less than.
Remember, the type of test is determined by what? So this would have a null hypothesis of what? Right? The mean is equal to some hypothesized means.
Right.
Right? And the alternative
Means it's
would
not.
be it's not.
Okay, so that is a two-tailed test.
That would be a two-tailed test. Okay. This is a right-tailed test. So the null is the mean is
It's greater than or equal to m0, which means it would be m is less than. Yeah.
Okay.
I thought we couldn't do less than or equal to on a alternative.
Well, the alternative does not have equality.
Right. Yeah. The
Always
alternative is just
inequality.
m is greater than m0.
It's always inequality. And this one would be the null is the mean would be greater than or equal to, and the alternative would be less than. Notice, and I said this before, but it's good to repeat it, okay? That the type of test is determined by the alternative. Right? It's determined by the alternative, right? Here the alternative is greater than. Here the alternative is less than. Right? We're looking for values less than our critical value. So the alternative determines the type of test, whether it's right-tailed, left-tailed, or two-tailed.
Okay, that makes a lot more sense now.
Yeah, you've got to focus on the alternative. Remember, the alternative is what we're collecting evidence about. We're collecting evidence in support, excuse me. We're collecting evidence in support of the alternative or against the null. But hypothesis testing is all about the alternative. My hypothesis testing is all about the alternative. Is everybody okay?
Yes.
Okay. How much area is here to the left of my critical value?
0.01.
Yeah, all of alpha, 0.01 is in here. And again, I'm going to want to compute a critical value. Okay, I'm going to want to compute a critical value here. And so just like we've seen before, right, I'm looking at the probability that I get a z value, but now I'm looking the other way, less than my critical value is equal to 0.01. Can I do less than in Excel?
Yeah.
So left-tailed test is the easiest because you don't have to worry about complements. You don't have to worry about splitting your alpha. You don't have to worry about anything. It's just simple. Right? So our critical value is just going to be norm.s.inverse of alpha. And they actually did this for some reason to 3 decimals. I'm not sure why they chose to do 3 decimals on this one. And I would call that a lower critical value to emphasize the fact that it's on the left of the mean. Is everybody okay with these?
Yeah.
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 So any questions on computing the test statistic, which you will have to do in most, if not, well, most, well, not necessarily all, because I'm going to show you an alternative that you can use in some cases. But a lot of cases, they're going to actually ask you in the problem for this number. And so you're going to have to compute it. Whenever you see a problem that says compute the test statistic, this is what they want, right? This is what they want, okay? This is the real test statistic. This is the real world value. You don't have to compute this. This is already computed. Okay, computing the test statistic means turning it into a z-score. Is everybody okay with that?
Yeah.
Okay, so recognize that when you see that in a problem on a homework or an exam, it means you have to do the conversion. Okay, you have to do the conversion. Is everybody okay so far? All doing okay so far? Okay, let's go back to the notes. Okay, and we'll continue on. And so now here's the thing that really bugs me about teaching hypothesis testing. And that is that whole idea of computing a test statistic and comparing it to a critical value. Nobody ever does that. Okay, nobody ever does that. I think in the past 5 to 10 years, I may have read one research study, and I can't remember whether it was medicine or something else, but I think I can only ever recall seeing a paper talk about a critical value once. Okay. In all the stuff I've read in the last 5 to 10 years, I can only recall seeing critical value once. Nobody does it. Okay. they do an approach called a p-value. Okay, they do this approach called a p-value. If you read any kind of research at all, you read any drug companies, tests of their drugs, they'll always have p-values. They'll never have critical values. Okay. So here's the thing about the p-value. If you can understand the p-value, you have got this down. Okay. Understanding the p-value, you've got this down. And it's the thing that a lot of people struggle with. There's lots and lots of stuff online explaining what p-values are because so many people have trouble understanding what p-values are. But here's the idea of the p-value. Let me do actually, let me use the one that I'd already drawn last time. Let me use the one that I drew last time. Okay. Where we have some, right? So we computed some critical values here. Okay. We computed some critical values and we have this test statistic. So the idea of the p-value, okay, what a p-value is it's the probability of getting a test statistic, right? Getting, in this case, a sample mean that's this far away from our hypothesized mean or further just by random chance. So that's what the p-value is. The p-value is what's the probability we get a value this far away from our hypothesized value or farther away just by random chance. Okay, because this is the distribution of all possible values. So there is non-zero probability of getting a value out here in either of the tails, isn't there?
Sorry, what was your question?
There is a non-zero probability of getting a value out in either of the tails.
Oh, yeah.
Absolutely, right? Because remember, these tails go on forever. Right? They go on forever. Forever that way, forever that way. They go on forever. Okay? And so there's non-zero area there. Okay? Although it gets really small really fast. And so when you compute a p-value, you compute the area. Okay, in this case, this would be a right-tailed test. You compute the area to the right of your test statistic. And that tells you how likely it is you got that value just by random chance. Does that make sense to everybody? Does everybody understand that?
Yeah.
Okay. And that means, what does it mean if your p-value is really small?
That there's a lower chance of it occurring or being that far away.
Yeah, exactly. It means that it's very unlikely that you got that just by chance. And if you didn't get it by chance, then you got it because it's meaningful. Does that make sense?
Yeah.
You got it because it's meaningful. So a small p-value means a high chance that this is wrong, that you can reject the null hypothesis. Okay, because a small p-value means it's very unlikely that you got this just by random chance. If you didn't get it by random chance, you got it because it's a meaningful number.
So small p-value means it's unlikely?
Yep. Because what the p-value is measuring is the probability that that number occurred just by random chance.
Ah, okay.
Right, so a small p-value means it's very unlikely that that occurred by random chance. Is everybody okay with that?
Yeah.
This is the way everybody does it. Okay, if you go look at, I can't even tell you how many research reports I looked at over the past 2 years on research about the coronavirus. Never saw a critical value in one of them. Lots and lots of p-values, but never a critical value. Okay, so that's the idea of the p-value. Okay, so the p-value measures the weight of evidence against the null hypothesis. Okay, it measures the weight of evidence against the null hypothesis. A very small p-value means it's very unlikely that occurred just by random chance, which means it's telling us something. Okay, and so what it's telling us, if we have a large p-value, like greater than 10%, right? That means there's greater than a 1 in 10 chance that it happened just by random chance. Okay, there's a greater than 1 in 10 probability it happened just by random chance. Okay, you consider that a good level of risk?
No.
No. Right? I would probably not want to take a 1 in 10 chance that I'm wrong. Okay, so that's really insufficient evidence against our null hypothesis. Now, when we get down between 5 and 10%, between a 1 in 10 and 1 in 20 chance, right? Then there's some evidence. It's not very strong, but there's a little bit, you know, depends on how much risk you're willing to take. Okay, but most of the time you see researchers and, you know, whoever's doing this looking for numbers less than 0.05. Okay, because less than 0.05 means less than a 1 in 20 chance, right? So there's pretty good evidence, right? Things that have a 1 in 20 chance don't happen very often. Okay, and then as your p-value gets smaller, I wouldn't use overwhelming for a 1% chance. I would probably call this very strong. Okay, but by the time we get down to 1 in 1,000, okay, do 1 in 1,000 things happen very often?
No.
No.
No. Okay, that's pretty rare. Okay, we would say this is really, really strong evidence, and the smaller that p-value gets, the stronger your evidence is that your null hypothesis is wrong. So the advantage of the p-value approach, okay, the advantage of the p-value approach is that we get a direct measure of how strong the evidence is. When we do the critical value approach, right, the critical value approach is just yes or no, do we reject, right? That's all we can say when we do the critical value approach is do we reject or not? There's no measure of how strong the evidence is. But when we do the p-value, that measures the strength of the evidence. And so I really like the p-value because it gives us that measure that we don't get when we take the critical value approach. And that's why everybody uses the p-value approach. Because when you read somebody's results and you see their p-value, you can use your knowledge and say, okay, did they come to a reasonable conclusion? Do I agree with their conclusion based on the level of evidence? Because now you have a measure of the level of evidence. Does that make sense to everybody?
Yeah. So the smaller the p-value, the stronger it is that H0 is false and the alternative is true.
Yes,
Okay.
exactly right. That's exactly right. Is everybody okay so far?
Yeah.
Okay. And then in terms of determining whether we reject or not, right? If my p-value is less than, remember, my area to the right of my critical value is my alpha, right? My area to the right of my critical value is my alpha. So all I have to do is take my p-value and compare it to my alpha. And if my p-value is less than my alpha, I reject, because it means my test statistic is in the rejection region. So not only do I get my decision, but I get a measure of how strong the evidence is in support of that decision. Is everybody okay?
Yeah.
Okay. Okay. So that's what the p-value is all about. Okay. That's what the p-value is all about. So should we do some practice?
Yeah.
Let's go back to our spreadsheet, and we'll start off with some simple practice where we just are given some numbers, and we need to compute the test statistic and the p-value. Notice here they actually tell you to compute the test statistic, right? So that means you have to compute this number. Okay, you have to compute that number. So I'm just going to copy these headings, and I think they'll, well, may not fit here, but let me start with that. Okay. So let's see, they give us alpha, and then yeah, so I'm going to rearrange these a little bit. Let's see, how do I want to rearrange these? That aligns with, oops, no, that's not quite right. Because those are backwards. There we go. Okay, so they give us this first one. Let me make sure I center everything. And so we've got 3 scenarios here. Actually, I'm going to do A twice because I want to show you something about A. Okay. So this first one, okay, the null hypothesis is that the mean is 60. The alternative is that the mean is not 60. The alpha is 0.025. The test statistic is 63. And they give us the population standard deviation and the sample size 8 and 16. Okay. What kind of a test is this? Is this a right-tailed, left-tailed, or two-tailed test?
This is a two-tailed test.
This is a two-tailed test. Okay, this is a two-tailed test. Okay, is everybody okay with that?
Yeah.
Okay. So this is the hardest one to do the textbook way with this is just the hardest one to do computing a p-value, because you have to pay really close attention to what's going on to make sure you do your computations correctly, because there are 3 different computations. Let's see, 3, 2. There are 2 different ways to do the computation. Okay, there are 2 different ways to do the computation. So that's why I duplicated this, so we can see both ways. Okay, so what's my hypothesized mean? That's just 60, right? Yes, no, maybe?
Yeah.
Hmm.
And then
Yeah.
standard error would be the
Yeah, how do you compute standard error?
The standard deviation divided by square root of n.
Right? And if you look at that without even doing any calculations in Excel, what's the standard error going to be?
2.
It's going to be 2. Right? Hopefully everybody sees that, because actually computing that 2, you could do in grade school. Because the square root of 16 is 4, and 8 divided by 4 is 2. Right? That's grade school math, right?
Mhm.
Okay,
Yes.
so there's our standard error. Okay. Can anybody tell me what the z-calc is going to be before we calculate it? Anybody? Nobody?
It wouldn't be negative.
Well, it's not going to be negative. Very good. It's going to be a positive, right? But can you tell me what the value is?
One and a half.
Yeah. How far is this from that? How
1.5.
How far is 63 from 60?
3 units.
3. How many standard errors is that?
That's 1.5.
It's 1.5. So how do I compute z-calc?
Standardized.
Standardize. Right? And oops, I put a minus in front instead of an equals. Equals. Standardized. And then what's my x value?
It's going to be x bar.
Yep. And what's my mean?
Mu 0 or mu
Yep.
naught.
And what's my standard deviation?
Standard error.
Standard error. And guess what we get? 1.5, just like we said we would. Right? These numbers are really nice because it all comes out really nice like this. So you can look at this and you should actually be able to get this far without actually even using a calculator, right?
Yeah.
But I will always, even when they're easy, I'll always do the right functions and formulas to calculate them. Okay, so we've computed the test statistic. That was the first thing they asked us to do.
Right.
Then they asked us to calculate the p-value. Okay, so how are we going to calculate the p-value? Okay, so let's go back and let's draw a little picture of this just to make sure we know what we're doing here. Okay. Okay, so we're using our standardized value, but I'm going to draw in the real world values first. Okay, our hypothesized mean is 60. Okay, we came up with a test statistic of 63, which is about 1.5 standard deviations from the mean. Okay, and the p-value is the area to the right of that. The probability of getting some value greater than 63 is the p-value. Oops, is it the p-value?
No, because we're doing the two-tail, right?
Yeah, very good. This is a two-tailed test. So we have to consider the fact that it's just as likely we got a number 3 above the mean as it is that we got a number
Yeah, 57.
3 below the
3
mean,
below.
isn't it? And so the p-value is really the area above 63 plus the area below 57. Is everybody following that?
Yeah.
Okay.
Yeah.
So that means because of symmetry, right? This area and that area are the same, aren't they?
So we only need to compute one.
Yeah, because this is the p-value over 2. This is half the p-value. So what we compute when we compute the area to the right is half the p-value. So we're going to need to remember when we compute that to multiply it by 2. Is everybody okay?
Yeah.
Yep.
Now we're actually using a standard normal distribution. So our actual mean of the distribution we're using to do our computations is 0. And we computed our z-calc at 1.5. And so here we'd be looking at the probability of getting a z-value greater than 1.5 is going to be our p-value over 2.
That's really good.
Now, can I do a greater than in Excel?
No.
No. So what do I have to do?
1 minus.
Yeah. So I have to do the complement, right? I've got to compute the probability of getting a value less than 1.5 is now 1 minus the P. Actually, I got to think about how to write this correctly. That's why it's 1 minus that equals the p-value over 2. There we go.
So it is p-value divided by 2, not 1 minus p-value minus divided by 2?
Well,
Oh, it's 1 minus p. Okay, that.
yeah, this is the p-value divided by 2. What we want is the p-value, so we're going to end up multiplying this by 2.
Okay.
We're going to take the complement, which is 1 minus the area to the left is the area to the right, and then we're going to multiply that by 2.
Okay.
Okay. So when I have multiple step computations like that, I like to do them in steps. So there's 3 parts to this. First, computing the area to the left. Second, turning that into the area to the right by taking the complement. And then the third is doubling it because it's a 2-tailed test. Does that make sense?
Yeah.
Yeah.
So first thing I'm going to do is, what function am I going to use to calculate my area to the left of my test statistic?
Norm.s inverse?
Well, I'm calculating area, not values.
Oh. Okay.
Standardized.
No. This is already a standardized value.
The norm.s.dist.
Yes. It needs to be a .dist function because I'm computing area. I'm computing probability from a value. Here's my value, and I want the area to the left of that value. So it's going to be a .dist function, and since it's a standard normal distribution that we're using, it's norm.s.dist.
And are we using cumulative distribution or probability density?
You tell me.
It doesn't say. I want to say we're looking at a probability density.
Nope.
Oh,
Oh,
so it is.
This is what kind of a distribution? It's continuous. In a continuous distribution, cumulative is always true. Remember I said that way back in chapter 7. In chapter 6, because that we were dealing with discrete distributions, we might use true, we might use false, depending on what we're looking for. But when you get to a continuous distribution, never, ever, ever use false. Because the probability density function does not give you probability. It gives you the height of the function, which is not probability.
Gotcha. Okay.
Okay. The height of the function is not probability. Okay. So with a probability density function, with a continuous distribution, cumulative is always true. Okay. So there's our area to the left. Then if I do 1 minus that, then I get the area to the right, And then remember to put your parentheses, right? I need to multiply that then by 2 to get the two-tailed p-value. And they did this to 4 decimals. There's my two-tailed p-value. Is everybody okay?
Yeah.
Okay. Now, do I reject or do I not reject?
Wait, go back to the p-value real quick.
Yep.
Because I just got the multiplied by 2. Oh, right, 1 minus and then times 2.
Right. Yeah.
Okay, there we go. If it's less than alpha, we reject. It's not less than alpha.
Bingo. So do I reject?
No.
No. Right. This number is clearly not less than that number. So we don't reject. So there's the p-value. And then there's our decision. Is everybody okay?
Yeah.
Okay. Now it turns out we could actually compute the p-value another way. Okay, we can compute the p-value without ever having to compute a test statistic. And this is the way I would do it in a problem that didn't require me to compute the test statistic. If I'm required to compute the test statistic, then I've got to compute the test statistic. If I don't have to compute the test statistic, I can actually compute the p-value. Can anybody guess how? Nobody? Well, I computed this value using norm.s.dist with my,
Oh, use norm.dist, but using the true.
that's exactly right. I can use norm.dist, norm.dist, right? And what's my x?
X bar,
Yep. What's my mean?
mu 0, and then
What's my
standard deviation. Would we be using the standard error or the normal standard deviation in this
Now
particular
you tell
case?
me.
I think we use the standard error.
Yes. We only use standard deviation to compute standard error. Once we've done that, we don't ever use it again. Right? And then cumulative,
True.
always true.
And then we can do,
And notice, oh, that's my left tail area. So I again need to do 1 minus to get my right tailed area. And this one's been giving me some problems. So I'm going to change the format right now. Before I do this. And then multiply by 2. And then those two, whoops, those two look the same. Whoops, one way. Those two look the same, don't they? But we can check
Yeah.
to see if they're the same by taking the difference and remembering to change the format to general. And they are exactly the same number. And so here I was able to do this without having to do that first. So here I had to do 2 steps. Here I only had to do 1 step. Okay, when I have a choice between 2 steps or 1 step, I will always choose 1 step. Because if you think about it, if you have 1 step, how many different ways can you make a mistake? You can only make a mistake in that step. But if you have 2 steps, you now could make a mistake in the first step or make a mistake in the second step. So I like less steps because it's less chance of making an error. Less chance of doing something wrong, entering a number wrong, hitting a key wrong that gives me a wrong answer. Is everybody okay?
Yeah, and you said this is, we can only really use this if we don't have to calculate the test statistic, right?
That's right. Yeah, so if you get a problem and they don't say compute the test statistic and it's not something you have to enter into Connect, you can actually do it this way. Okay. This will always give you the right answer. So if you if you understand this and you're comfortable doing this, then you can continue to do that. Okay. You can do it either way, except when they ask for a test statistic, you have to compute it this way.
Great, thank you.
Okay. Now we said we could have gotten the same result, right? We could have gotten the same result with a sample mean of 57, right?
Yeah,
Right? Because the p-value, right? The p-value is what's the probability of getting a value this extreme or more extreme, which in a two-tailed test includes this value and that area. So what if we had gotten a 57? What if our sample mean had been 57?
No, the only thing
How different would this p-value be?
is just the negative, right?
No? P-value is probability. Can probabilities ever be negative?
Oh, no. It's gonna be just 1 minus that, right?
Nope. If, let's just call that 13%. If 13% is the probability of getting a value over here or over there, what's the probability of getting a value over here or over there?
About 13. About
So what's-
13.
So what's my p-value going to be?
It'll be the same.
It'll be the same. Okay. What's my standard error going to be?
The same.
The same. What's my z-calc going to be?
Oh, the same.
Be careful.
It's the negative of that.
It's going to be negative 1.5. Whoops. Because I'm now on the other side. Okay, because I'm now on the other side of the mean. So it's going to be negative 1.5. And then my p-value, well, this calculation is not going to work because the calculation I did reflects the fact that I got a value above the mean. So doing 1 minus, right, 1 minus the probability over there is going to give me the probability over there, and that's not what I want. So I'm now on the other side of the mean. So now I'm looking at the probability of getting a value less than 57. That's my p-value over 2. Which in standard normal terms means the probability of getting a z-value less than, in this case, negative 1.5, negative 1.5, okay, is equal to my p-value over 2. So I need to take a complement in this case?
No.
No. Okay. So notice, okay, you have to be very careful when you're doing a two-tailed test because you could get a value above the mean or you could get a value below the mean, and how you calculate the p-value is different if you get a value above the mean or you get a value below the mean. In either case, we're still going to have to multiply by 2. It's just that if we get a value below the mean, we don't have to take the complement, right? So I just do norm.s.dist of my negative z-value, and cumulative is true, and now I just double this. No complement required. I take the color off that because this is an extra one. And then this says exactly the same thing, right? My p-value is not less than my alpha, so I don't reject. I get the same conclusion. And if I don't use the standardized test statistic, I can still do norm.dist exactly like I did, but now I don't have to take the complement. I just have to double it. And then we can check and see, are those two numbers equal? Do a format copy here. It's easier. They're exactly the same. How about these two? Are those two numbers equal? Format copy. They're exactly the same. So again, I just can't overemphasize this. When you have a two-tailed hypothesis test and you're computing a p-value, you've got to pay attention to whether your sample mean or your sample statistic is above your hypothesized value or below your hypothesized value, okay? Because that affects how you calculate the area. But you always have to multiply by 2 because it's a two-tailed test, and you have to consider both extremes, both below and above. Does that make sense?
Yeah.
Okay. So keep that in mind when you're doing a two-tailed test. Okay, whenever you have a two-tailed test, okay, if your mean is above, you need to take the complement and then multiply by 2. If your mean is below, then you don't need to take the complement. You just compute the area and then multiply by 2. And that gives you your p-value. And so if you're doing a two-tailed test in Connect and you do a check my work and it tells you you're wrong, check and make sure you multiplied your p-value by 2. Are we okay?
Yeah, I just have a quick question, and
Yes.
and it's an easy one, but it's slipping my mind. How do we know we reject? I know it's just we compare the number to something.
Yeah, we compare the p-value to alpha.
Okay, and in this case, since it's the two-tailed test, it's just whether it equals alpha or not, right?
No, it's we reject if the p-value is less than alpha.
If you guys know.
Actually, I wrote that here. We reject if the p-value is less than alpha.
Oh, okay, okay.
That's the other nice thing about p-values is it's always the same. We don't have to look to see, you know, are we above this? Are we below this? We don't have to look to see where we are. All we do is compute the p-value. That's some area. We compare it to the area of alpha. And if the p-value area is less than the area of alpha, we reject. Period.
Okay,
Doesn't matter
cool.
the kind of test. Two-tailed, right-tailed, left-tailed. It's always the same rejection rule,
Okay, that's easy.
right? If we do the critical value approach, we've got to look and see, right? Are we doing a right-tailed test? Are we doing a left-tailed test? Are we doing a two-tailed test? Where is our value falling? Is it in the rejection region, right? We've got to pay attention to all that detail. With a p-value approach, we compute the p-value, we compare it to alpha. If it's less than alpha, we reject. The end.
Perfect. Sounds good. Thank you.
It's a really easy approach. And it's that, you know, there's lots of reasons why it's preferable to the critical value approach. Ready to go on?
Yeah.
Okay. So B, the null hypothesis is that the mean is greater than or equal to 60. The alternative is that it's less than 60. Is this a right-tailed, left-tailed, or two-tailed test?
Would it be a left tail?
Yeah. Because remember, it's determined by the alternative, right? Less than would be a left-tailed test. Okay. So they give us the mean. I'm just going to type it in, right? 60. they give us the alpha. This alpha is 0.05. They give us our test statistic is 58. They give us our standard deviation is 5. And they give us our sample size is 25, which means without doing any calculator or Excel, what's my standard error going to be?
1.
It's going to be 1. Right? Square root of 25 is 5. 5 divided by 5 is 1. Okay. Again, without doing any calculations in Excel or on a calculator, what's my z-score going to be?
Be -2.
-2. Okay. Because this is 2 below that, and 2 is 2 standard errors. And since it's below, it's negative. Okay. So there's the calculation, right, of standard error. And there's the calculation, right, of our test statistic. But with these numbers, we could actually just do those in our head, right?
Yeah.
Everybody okay?
Yep.
Okay, so let's draw a picture. Okay, before we try to finish this, let's draw a picture. And so, again, I'm going to draw in first the real world values, right? We've got a hypothesized mean of 60. We're doing a left-tailed test, okay? And we came out with a test statistic that's like somewhere over here, right? Our X bar is 58. And so what we want to do is then we want to compute the p-value, which is the probability of getting a value less than 58, is just going to be my p-value, huh? That's an easy one, right?
Yeah.
So what we'll do, because they require a test statistic, is we'll convert everything to standard normal. So we'll compute our z-calc, which we already did, right? Our z-calc came out to be -2. Okay. And so our computation of our p-value is we're looking at the probability of getting a z-value less than -2 is equal to our p-value. Can I do this in Excel?
Yeah.
Yeah. And actually, without even calculating it, can you tell me approximately what that p-value is going to be?
Around 0.3.
Nope. How much area is within 2 standard deviations of the mean? Y'all should know the answer to this. Every single one of you should know the answer to this, because I've told you over and over, memorize this.
95%.
95%, exactly. If 95% is between, how much is in one tail?
2.5%.
2.5%. So this should be close to 0.025. It's going to be a little less because we rounded the 95. It's actually 95 point something, right? So it's going to be a little less, but it's going to be close, right? So we should get a number very close to 0.025. So let's see what we get. Okay. So norm.s.dist.
You're still on the cam.
Yeah, thanks. Back to Excel. Norm.s.dist of our z-score, and cumulative is true. Is everybody okay?
Yeah.
Okay. And there we go. And That's very close to 0.025. Again, it's a little less because we round the 95%. It's really 95 point something something. I think it's 95.44 if I'm not mistaken. But we just use 95 because that's close enough. Right? We're only ever going to use that to approximate anyway. And so that's a good approximation. Right? And so this looks like it should look, doesn't it?
Yeah.
Okay. It looks like it should look. Okay. And they actually did this one to 5 decimals. They actually left this 5 decimals. So do we reject or not?
Yes.
Why?
Because it's less than alpha.
That's right. This number is smaller than that number. Therefore, we reject. Does that make sense?
Yes.
And we could also have computed, just like before, we also could have computed our p-value. Why does it do that? Okay, we could have also computed our p-value using norm.dist and just using our real values. Right, there's our mean, there's our hypothesized value, there's our standard error. Make sure I get the right one for standard error. And then cumulative is true, and then we get the same value. Right, and we can check, are those numbers equal? Yes, they're exactly equal. Are we okay?
Yeah.
Okay. Any questions on this one before we go to the last one? Okay, if everybody's okay. So the last one says the null hypothesis is that the mean is less than or equal to 60. The alternative is that it's greater than 60. So is this a right tail, left tail, or two-tail test?
Right tail.
This is right tail, isn't it?
Yeah.
As it's greater than, the alternative is greater than. Remember, the alternative determines the type of test. So this is a right tail test. So we've got a hypothesized value of 60. We've got an alpha, again, of 0.05. Now we've got a mean, a sample mean is 65, and our population standard deviation is 8, and our sample size is 36, which, can anybody do that math?
About 1.3.
Yeah, it's 1 1/3. It's 1 1/3. Okay. Anybody want to try and do this one without using Excel or a calculator? It's a little bit harder, but it can actually be done.
Well, it's going to be a positive number.
It's going to be a positive
Yeah.
number. Very good. Can you tell me the value?
Let's see, what was the standardized function?
So remember, what's the Z telling us? How many standard deviations this number is away from that?
Right.
Number? How far are those numbers apart?
Wait, and if it's 1.3, it's 5 apart. So that's 1, 2. Less than 4, but more than 3.
Yeah. Well, actually, if you think about it, 3 times this is 4.
Right.
Right? And then that leaves 1 left over, and 1 over this, right? 1 has 3/3. This has 4/3. So that's 3/4.
So 0.75. So 3.75 then?
3.75. Very good.
Oh, cool.
3.75. Okay. Is everybody okay?
Yeah.
Okay.
Yep.
So let's again draw our picture. Okay, so we make sure we know what we're talking about here. Okay, so again, we've got our hypothesized value of 60. Okay, this time it's a right-tailed test, and our sample value 65, we already know is pretty far away, right? It's almost 4 standard deviations away from the mean, right? It's pretty far away. Our X bar over here at 65 is pretty far away, okay? And our P value here, is it going to be large or small?
It's small.
It's going to be pretty small, isn't it? Right? We already can tell because if it were 3 standard deviations away from the mean, the P value would be 0.00135. But this is even farther away than that. So this is going to be even smaller than that. Okay? So this is one of those circumstances where let's compute the P value. The P value is the probability of getting a value greater than 65 is our P value. Okay. And so can I do a greater than?
No.
No, so I'm going to have to do the complement, right? So let's convert our numbers to standard normal numbers, right? Our mean is 0. And we already computed the z-calc is 3.75, right? So what we're trying to find out is the probability that we get a z-value greater than 3.75, and that's our p-value. And so we know, can we take it, can we do a greater than in Excel?
No.
No, so we have to do
Complement.
the complement, right? So we have to do the complement. So our p-value is going to be 1 minus the probability of z less than 3.75. That's going to be our p-value. Are we okay?
Yeah.
Okay. So let's go back to Excel and do the computation. Okay, so my p-value, and again, I always like to do this in steps. So first I'm going to compute the area to the left, norm.s.dist. Okay, so the area to the left, I need my z-value, and cumulative is true. Everybody okay?
Yeah.
Okay, but then I need to take the complement of that. So I'll go in here and I'll plug in my 1 minus. Okay, oops, it's doing that again. I hate that. So let me change the format. Every once in a while it does that. It'll decide it wants to make my column wider, and I don't want my columns wider. I want them this width. So there's my p-value. So do I reject?
Yeah.
Okay. How strong is the evidence against my null hypothesis?
Very strong.
It's very strong. Okay. This is saying I'm almost 100% certain this is not right. Okay. I'm almost 100% certain. Okay. Because this is what, 9 in, what is that? Tens, hundreds, thousands, 10,000s? That's 9 in 100,000, or less than 1 in 10,000 chance. Okay, less than 1 in 10,000 times that you do this test, you're going to come up with a value that just shows up by random chance. That's pretty rare, isn't it?
Yeah.
Yeah.
Okay, so you would say there's, this is, I might even say this is beyond overwhelming. Okay, this is just incredibly, unbelievably strong evidence that our null hypothesis is wrong. And again, I can compute that same number using norm.dist and our real values. And then to avoid the problem, I'm actually going to just copy the format. And I'll get rid of the yellow in a minute, and then do 1 minus. Do the complement. Bingo. And then we can check, are they the same? Yeah, they're the same. How we doing?
Good.
Good so far.
Okay. Okay, so this was really nice and neat because you were just given a bunch of values. Okay. But that's not realistic. Right? Your boss is never going to come to you and throw a piece of paper on your desk with numbers like this and say, compute the p-value. Okay. You're going to have to come up with the hypotheses. You're going to have to determine the appropriate alpha. You're going to have to go out and do the sample. Okay. You're going to have to do all the work. Okay. Nobody's going to lay it in your lap. So it's going to be a little closer to this. Not quite, but a little closer to this. Okay. Where we've got a company that makes tennis balls. The tennis ball weights are supposed to be normally distributed with a mean of 2.35 ounces and a standard deviation of 0.002 ounces. Okay. Very precise weight requirements. A sample of 25 tennis balls shows a mean weight of 2.036 ounces at an alpha of 0.025. And now here's where they do stuff in the textbook that I think just is a bad idea. Okay. And here they tell you, what kind of a test is this?
All right, too.
Okay. But do they need to tell you that?
No.
No, because what does the next part of the sentence say?
Is it heavier?
Okay.
Is the mean weight heavier?
That's redundant, right? Because asking if the mean weight is heavier than it's supposed to be means it's a right-tailed test. Okay? So be careful because, say, on an exam, I'm not likely to tell you this. Okay? And I guarantee you when you get to your next class, they will never tell you that. Okay? It won't be in the homework, won't be in the exams, won't be anywhere. You'll have to figure out whether it's a right-tailed, left-tailed, or two-tailed test. Okay? So this is clearly a right-tailed test because what's interesting? Is it interesting when the weights of the tennis balls are what they're supposed to be?
No.
No.
It's that it's heavier than it's supposed to
That's
be.
right. It's interesting when they're not the right weights. In this case, we're interested in when they're heavier, right?
So
That's what becomes interesting.
let's say in a future class, then they wouldn't say right-tailed test. They'd probably only have, is the mean weight heavier than it's supposed to be? And you'd be able to
Exactly.
figure out.
That's right. That's right. And so what you need to do is you need to ask, what's the interesting case? The interesting case, if you think about it, as long as the mean weight is 2.035 ounces, you're sitting back with your feet up on your desk doing nothing. Right?
Okay.
Playing games on your phone. The minute that it's not, the minute that the mean weight is higher, are you still sitting back in your chair playing games on your phone?
No.
Oh, you're figuring.
No, you're up trying to find the problem and fix it, aren't you? That's the interesting case. Does that make
Okay.
sense?
Yeah.
Yes.
The interesting case usually leads to action, right? It's what leads to action. Okay. So they give us some information here. Okay. They tell, let's actually write down the null and alternative hypotheses to start. Let's actually write them down. The null and alternative hypotheses to start. Okay, so we'll put in the null and alternative hypotheses. Okay, and then we need then from that we'll get our hypothesized mean. U naught. Okay, and they give us our standard deviation. Okay, and they tell us we took a sample of 25. They give us the sample size. They tell us our sample mean, X bar, and they give us our alpha of 0.025. Okay, so who wants to take a shot at giving me either the null or the alternative? Anybody want to take a shot at giving me either the null or alternative hypotheses?
I'll try the alternative.
What's
Is
the
it the-
alternative?
That X bar is greater than 2.035.
Okay, almost. You know what you did wrong there? We're not hypothesizing about the sample mean.
Oh, we're just doing the mean.
Yeah.
So the mu is greater
Yes.
than.
We're hypothesizing. Remember, we're always hypothesizing about the population. We're going to know what the sample is. We're hypothesizing about the population. Okay, so it's mu. Exactly. It's mu is greater than 2.035. Exactly. That's
That
exact-
means H naught is mu is less than or equal to 2.035.
Bingo. Okay, and by the way, this is exactly how I would do it. I would come up with the alternative first. I almost always find it easier to come up with this first. This is almost always the easiest thing because it's the interesting thing. It's the thing that we care about. Right? It's what we care about. And so we can usually figure out pretty easily what we care about, and that's the alternative. Is everybody okay?
Yeah.
Okay, so that means our hypothesized value is the 2.035. That's going to be the mean. Oops. 2.035. That's going to be the mean of our sampling distribution. Okay, and then they give us our sample standard deviation 0.002, and they give us our sample size. They told us we took a sample of 25 tennis balls, and they told us the average weight of those tennis balls is 2.036. Okay, and they give us an alpha of 0.025. Okay, now you have to be careful because do those two numbers look like they're very far apart?
No.
No. Right? So if you just looked at those numbers, you would look at them and say, well, you know, is that really that different?
But the standard deviation is very small.
Standard deviation is very small, but is standard deviation what counts?
No, it'll be the standard error.
Bingo! Bingo! It's the standard error that counts because the distribution we're looking at is the sampling distribution. And the sampling distribution does not have that as a standard deviation. It has standard error. And how do we compute standard error?
It is the standard deviation divided by the square root of n.
Right? And if you do that in your head, square root of 25 is 5. 0.002 divided by 5 is 0.0004, I think, right? Yeah, that's what it is. Okay.
That's even
That's-
smaller.
Yeah. Now, does that difference look very big?
Yes, very much.
Yes.
It does. As a matter of fact, right? How many standard errors is that? What's my z-calc going to be? Can you do my z-calc without doing the standardized function? What's the difference between these two numbers?
0.1, 0.001, sorry.
Yeah, 0.001, okay?
0.001, and that's 0.0004.
Yeah, so
That's-
now do this. Multiply both those values by 10,000. 0.001 times 10,000 is 10. 0.0004 times 10,000 is 4.
At 2.5.
2.5. Let's see, do we get 2.5? There's our sample mean. There's our hypothesis, whoops, there's our hypothesized value. And there's our standard error. And what do we get? Oh, look, we get 2.5, just like we said.
So yeah, it's definitely heavier than it's supposed to be.
Yeah, right? 2.5 standard deviations is kind of far out, isn't it? Okay. So let's compute. So notice this problem. So this is what I want you to pay attention to when you're doing problems in Connect. This problem doesn't tell you how to do it. Do you notice that?
Yeah.
It doesn't tell you how to do it. So if Connect doesn't require you to enter this value, you don't need to compute it. But if you want to, you can. Right? So I'm going to do it this way because this is the way it's done in the book. Okay. How do I compute the p-value? Well,
Norm.s.dist.
yeah. So let's draw the picture before we go on any farther. Okay. So what we've got is we've got our actual mean, our actual hypothesized mean is 2.035. Okay, and we got this value out here, our sample mean of 2.036. Okay, and we want a p-value, which is the area to the right of that. Our p-value is the probability of getting a value greater than 2.036. Okay, and so if we convert these to standard normal, mean is 0. We computed our z-calc here, 2.5. And so probability of getting a z-value greater than 2.5 is our p-value. Can I do greater than?
No.
So how do I do it?
The complement.
Take the complement. Okay, so we'll do exactly like we did before. And I always do this in multiple steps. I'm always going to compute the area to the left first. Okay, and then I'm going to take the complement. And there's our p-value. And so do I reject?
Yes,
Why?
because our p-value is less than 0.025.
Yeah, our p-value is less than alpha. Does everybody see that?
Yeah.
Okay. So that means what's our conclusion? R is the mean weight heavier than it's supposed to be?
Yes.
Yes. Right. And that's pretty good. That's pretty good evidence. Right. That's pretty good evidence. Okay. That might justify shutting down the production line to fix whatever the problem is. Because that's pretty good evidence that we're not producing tennis balls that are at the right weight. Okay. Are those kinds of things important?
Yeah.
If you're making tennis balls, where would you want your tennis balls to be used?
The biggest tournament.
Biggest tournaments, right? Are the biggest tournaments just going to use anybody's tennis balls? Do they just say,
No.
you know, a tennis ball can be anything? We don't care how big it is, how small it is, how much it weighs?
No, there's a standard.
That's right. Tournaments have standards. And if you don't meet the standards, you don't get to have your equipment used in the tournament. And so companies are always trying to find ways to improve their product, but still meet the standards that are required by the standard setting bodies for the tournaments. Is everybody okay?
Yeah.
Okay. And again, they didn't tell us how to do this, so I could have avoided doing that just by doing norm.dist. right? And my sample mean and my hypothesized value and my standard error and my cumulative, oops. Yes, thank you. And my cumulative flag, boom. And then take the complement and I get the same value. How are we doing?
Good.
Doing okay?
So far, good.
So far, so good? Any questions on this one?
I don't think so.
Okay. Okay. If not, we've only got a couple of minutes left. So we're not going to have time to do this. So I'm going to ask you to do this for our next class. Okay. This is a two-tailed test. They give you, right, what the average contents are supposed to be. The bottles of water are supposed to contain 10 ounces. The filling process has a normal distribution with a standard deviation of 0.07 ounces. We took a random sample of 12 bottles, and we want to do a two-tailed test at 5% to determine whether we're actually filling the bottles at 10 ounces. Okay. Why is this two-tailed?
Because too much or too little is an error.
Yeah, both of those are big problems, aren't they? Right? If we're putting too little in, then we're not giving customers what we're claiming. If we put too much in, then we're overfilling the bottles and we're wasting product. Does that make sense?
Yeah.
So we care about both ends in this case. So quality control statistics like this are typically two-tailed tests, right? They're typically two-tailed tests because we care about both directions. Okay. It turns out that there is a file called bottle fill that contains the data if you want to use it. It's in the chapter 9 exercises folder. Okay. But what I would do if I were doing this, and actually this is what I'm going to do. I'm going to do it right now. I would take these numbers, copy them, go back to our spreadsheet, and then in this first row below the problem, I would do paste special and transpose, right? So it doesn't take up much room, just take up a line. And then I'm going to get rid of the borders because it copied the borders too. So I'm just going to get rid of the borders. And then, okay, you're going to have to calculate the test statistic, right? You're going to have to actually calculate the sample statistic and then do the test. Okay. So what I would suggest is do like we did up here. Okay. Do like we did up here, where we first started with determine the null and alternative hypotheses. Okay. Then what is the mean of our hypothesized distribution, standard deviation, sample size, sample mean, okay, alpha, and then you can actually compute the rest of the values to determine whether we reject or not. Is everybody okay?
Yep.
Okay. So, and then when we come back, okay, everybody knows there's no class next week, right?
Wait, the whole week?
All week.
Thanksgiving,
Oh.
right?
Yeah, yeah. A couple of years ago, Palomar started just taking the entire week off. So there are no classes next week, so we will not meet next Tuesday. Our next meeting will be the 30th after Thanksgiving.
Oh,
Okay?
wow. Okay.
So please remember to do this over the break, right? Put it in your calendar for Sunday or Monday or something like that so you remember to do it. Because what I want to do when you come back is look at that two-tailed test. And then I'm going to ask you a quick question right now. See if you can answer this. Does this look like anything, right? Where I've got a lower critical value and I've got an upper critical value.